the homework assignment in the WeChat group, and you're supposed to finish 3 questions. You can either prepare your answer sheet in PDF or Word file, or you can do it by handwriting and then take a photograph. I think both methods should be okay. Okay, so it's up to you how you're gonna prepare your answers. But anyway, you are expected to send your you can see the PDF format. It could be handwritten, it could be typing and electrically prepared. It's fine. So anyway, it's a single PDF format to this email address by the end of October. So you have 1 month to more than 1 month to finish your homework. Yeah, so it's very how to say, it's very relaxed. Okay, so you have sufficient time to prepare your homework. And okay, so everything clear? If anything is not clear, could you please, you can just let me know. Okay, so you can let me know now. Okay, if everything is clear, we are going to start today's lecture. Okay, in the previous lecture, we have discussed the following issues. First of all, we introduced rigid plastic assumption, and then we introduced the concept of plastic hinge, and then we briefly present the concepts of statically determinate and statically indeterminate structure, and how and why these 2 types of structures they have different behavior, especially the redundancy. Okay, just do you remember, for statically determinate structure, if one member fails or one member yields or one cross-section fails, the whole system will come into a mechanism. So they basically they will collapse. However, for statically indeterminate structure, because of the extra redundancy, even if one section or more than one section experiences plastic hinge, the whole system may still be able to keep carrying loads until the necessary number of plastic hinges, take a beam for example, until a necessary number of plastic hinges form, and then the whole system collapses. Okay, and then we introduce a very, very important methods, which is called kinematic analysis method, to determine the collapse load of a, say, beam. So kinematic analysis, the basic concept is that the work down by the applied load equals to the internal energy dissipation or energy absorbed by all the plastic hinges. So if this condition is satisfied, and the structure, we can say that this structure is in a collapse condition, which means we can use this equation to obtain the collapse load, right? So this is the basic concept. It's a very easy concept. It is based on the principle of virtual work. So it's quite straightforward, actually. It's not difficult. But what we will discuss today, we will discuss 2 things. First thing is, okay, so for a simple beam, especially for those under point load, right? It is very, very easy to predict the location of plastic hinges, right? Because we can use our structural common sense. We can just, use our experience, our knowledge to predict or determine the possible location of the plastic hinges. And normally it's precise, it's correct. However, for more complicated cases, for example, a beam under a complex distributed load, UDL, uniform distributed load, sometimes it is difficult to give the exact location of the plastic hinges, right? Because this is the condition that you're going to face when you design a beam. This is a very typical condition that you are not able to quickly locate the exact location of the plastic hinges. So in this case, what will you do? Okay, so this is the first question that we will answer in today's lecture. Actually, it's okay. You can imagine, okay, if you choose the right position, choose the right location of plastic hinges, you can still use a kinematic analysis. Even if you choose the wrong one, you can still use a kinematic analysis, and you will get some upper or lower bound results, and then make some adjustment, and then you will get the final results. Okay, so I'm going to discuss these in detail later on. And second question that we could answer from today's lecture is we will look at a frame, okay? Because we start from a beam. A beam is a very simple example of a structural member, right? And then we will extend our knowledge to see how we can solve such problems in a simple portal frame. Okay, so these are the two major objectives of today's lecture. So in the first half of today's lecture, we would further discuss plastic collapse mechanisms. These are typical mechanisms. And then we use kinematic analysis to do some further, to deal with some further problems. And then we will introduce some theorems of plastic analysis. And finally, we will quickly go through some design aspects. Okay. So based on the rigid plastic assumption, which we have already discussed it in last week, so plastic methods target aims to determine the collapse load, PC, right? P collapse load, PC, at which a collapse mechanism first forms. Only the final mechanism condition must be found, and any intermediate load conditions can actually be ignored. Okay, so do you remember in last week, what we did is we first found first hinge load, right? Do you remember that? P1. And then we get PC, and then we compare P1 and PC. Of course, PCs must be larger than P1, right? That's what we did in last week. But however, from today's class, what you need to do is you just need to find the PC. That's enough. You don't need to find P1, because finding P1, as I mentioned, is just used to show you, okay, the reserve, how much reserve we can have after first yielding. Okay, so this is just an illustration, but from our point of view, it's not necessary, because what we finally need to do is we just want to find PC. Okay, so that's the final objective, and that's a key objective. So from now on, you just don't need to find P1, because that's the first yielding load, and it's sometimes unnecessary to bother finding P1, right? So what we need to do is just finding PC. That's very important. So under a collapse condition, the beam is a mechanism, right? And when a beam becomes a mechanism, it becomes a statically determinate. And the behavior can be analyzed by statics. So here is some examples that you should be familiar with. The most typical mechanism for a beam is called two-bar mechanism. This is the most typical one. So either plastic hinge or frictionless hinge at each support plus a plastic hinge within the span. So for example, this is a simply supported beam, and then we have a simple, we have a point load applied at the middle span, and then we will have one plastic hinge here and two frictionless hinges at the support, so which we form a two-bar mechanism, right? Similarly, we have a propped cantilever. So this is a fixed end, this is a simple support. And similarly, we have one plastic hinge here and one plastic hinge here, and we form a two-bar mechanism again. And similarly here, fixed end, point load. So also three plastic hinges and two-bar mechanism. So these pictures, these photo illustrations shows you the typical two-bar mechanism. Of course, if we are dealing with multi-span beams, we can also give some predictions. Use our knowledge, use our experience to find the right two-bar mechanism. For example, if there are two span beams, and there's one P1 and P2, 2-point loads. If P1 is much larger than P2, so we should have this mechanism. This is two-bar mechanism, right? Or if P2 is much larger than P1, similarly, we can have such mechanism. Of course, if P1 is exact the same as P2, maybe there will be like this and this. Or two adjacent spans may combine to form a three-bar mechanism. This is a very special condition. If we have a one-point load here and another point load in the opposite direction, so we may have a three-bar mechanism, but this is not very typical in real structures, right? These are more typical, more common in structures. But anyway, regardless of the combination of these loads, I think you should be able to identify these two-bar or three-bar mechanism. And these will form the basis of the following calculations when you use kinematic analysis, okay, kinematic method. So for plastic hinge locations, okay, so based on the previous examples, two-bar mechanism and three-bar mechanism examples, we can say the potential locations for plastic hinges may be at the supports, maybe at the points of concentrated point load, or this is less common, but it is possible, the point of cross-section change. Okay, if a beam has two cross-sections, the cross-section change could have plastic hinges. However, as I mentioned, the exact location of the plastic hinge with distributed load is often not well defined. I'm going to show you an example later on, except with the help of symmetry. But of course, for certain conditions, we may be able to determine the exact location of plastic hinges, but for most cases, it's quite difficult. Of course, we can guess. We can just guess, okay, the plastic hinge may be near here. Yes, we can guess, but it is difficult to find the 100% exact location. It's difficult. Okay, so what we could do, we could guess. We could assume a location of plastic hinges. And then we use kinematic analysis. I'm going to show you later on. And then we try to, this is very important. This is the key of today's lecture, we try to validate the following three conditions: equilibrium condition, mechanism condition, and yield condition. Okay, so first I will go through these conditions. Maybe you don't know what exactly what are they, but I will explain this later on. But first of all, just to quickly go through the three conditions and let you know that there will be three conditions that you need to understand. The first is equilibrium. Actually, equilibrium condition is not a problem, because when you make calculations, you always follow equilibrium principle, right? So the first condition is always satisfied. Normally, it should not be a problem. The second condition, mechanism. Okay, mechanism means you must have sufficient number of plastic hinges to form a final mechanism to collapse, right? And third, the yield condition is if you draw a bending moment diagram based on the plastic hinges and equilibrium. If you draw a bending moment diagram, this bending moment diagram should always be less than MPL. Bending moment diagram should always be less than the plastic moment resistance of the cross section, MPL. Because these are three conditions. If all the three conditions are satisfied, your location is right. You mean you have the right exact 100% exact location, and the result PC, the resulting PC is exactly the correct one. Okay. So first, we'll quickly go through the first condition, the equilibrium condition. Let's assume a simply supported beam. The bending moment distribution defined by the assumed plastic hinges must be in static equilibrium with applied loads and reactions. So for example, we have a plastic hinge here, right? This is bending moment diagram. And then we have MPL, right? Because it's a plastic hinge, so we have MPL here. And then we maybe isolate this beam, this part of the beam, and we can get PC. And it's very simple. So we have bending moment here, MPL, which is equals to PC over 2 because of symmetry. This is PC, this is half PC. PC over 2 times this distance. I think it's L over 2, right? So then based on this equilibrium, we can get PC, which is 4 MPL over L, right? So it's very simple. What you need to do is make a free body diagram of a isolated part of the beam and make it equilibrium, make it a equilibrium condition. So in other words, if you make these conditions, if you make these calculations based on equilibrium, this condition, equilibrium condition, is always satisfied. So you don't need to worry about that. Okay, how about mechanism condition? So there must be, as I mentioned, there must be a sufficient number of plastic hinges and frictionless hinges for the beam to form a mechanism. This condition is usually satisfied directly by the choice of hinges. So for example, if you want to make a 2-bar mechanism, you should know which location should have hinges. Okay, so you guess. So normally it should be fine. So sufficient plastic hinges and frictionless hinges means that the mechanism condition is satisfied. How about yield condition? The full plastic moment of every cross-section must not be exceeded. So along the bending moment diagram, every point in this bending moment diagram, the absolute value should be less than MPL. Right? For example, this bending moment diagram, all the bending moments along the beam length is less than MPL. So yield condition is satisfied. Okay, it's also very easy. So if all the three conditions are satisfied, remember this one will be the true one, and this location is the right location. Okay, it sounds easy, right? It sounds easy, but actually, when we meet with more complicated problems, it's not that easy. But it's fine. It's fine. Let's continue. Okay, let's see what happens. So here we have extra theorems of plastic hinges that you need to remember. Sorry, the plastic analysis that you need to remember. First, Based on the satisfaction of the aforementioned three conditions, three theorems of plastic hinges are developed, which are uniqueness theorem, lower bound theorem, and upper bound theorem. What is uniqueness theorem? If the assumed plastic hinges satisfy these three conditions simultaneously, satisfy, they are the correct ones, and they define the plastic mechanism in the beam. And the resulting PC can be determined from the equilibrium conditions. This is a uniqueness theorem, which I have already mentioned before. So in other words, it is not possible to obtain another mechanism which satisfies all three conditions simultaneously, right? So it's called a unique. There's only one possible condition that satisfies all the three conditions. And the collapse load determined is a unique solution. Okay, this is a unique solution. If satisfied, mechanism condition satisfied, yield condition satisfied, you get a unique solution and the correct solution, PC. Okay, so as I meant, for example, this is a simply supported beam and everything is satisfied, and you will get the right one, the unique solution. Okay, what is upper bound theorem? Upper bound theorem means you will get upper bound value. Sometimes it is possible to assume more than one series of plastic hinges, and so while the assumed plastic hinges may satisfy the equilibrium and the mechanism condition because you have sufficient number of plastic hinges, right? So you satisfy equilibrium, you satisfy the mechanism condition, but the yield condition may be violated. So if this is the condition, you will get an upper bound value of PC. So the corresponding load calculated from the equilibrium condition is greater than the true collapse load. Okay, for example, if this is a simply supported beam, and you assume plastic hinges happens here, and then you will get PC, right? And this is the right and the unique answer, right? Okay, how about say, okay, no, I don't want plastic hinges here. I want plastic hinges here. The point load is here, but plastic hinges here, and then you use the the kinematic analysis, right? And then you'll get another PC. Okay, you'll get another PC, and that PC must be larger than the unique value, the unique solution. So that PC is the upper bound result. Can all of you mute yourself, please? I think some students, please mute yourself. Yes, good, good. Okay. Upper bound theorem. Yes, this is upper bound theorem. So, mechanism method, upper bound solution. So if you satisfy equilibrium condition, you satisfy mechanism condition, and yield condition is violated, you get upper bound theorem, upper bound result. Let me show you an example of getting an upper bound result. Okay. This is a beam. We have 3 points, 1, 2, 3, 4, and this is 1/3 of L, 1/3 of L, and 1/3 of L. Okay, so there are 2 point loads applied at 1/3 of span. This is P, and this is 2P. Okay, so first of all, this is the beam, and based on the two-bar mechanism, how many plastic hinges there should be? Can you type it down? How many plastic hinges you expect in this beam? Don't worry, forget about these Forget about this, okay? So just based on this, how many plastic hinges you expect? Okay, no, it's, oh yeah. Some people say it's 4. 4 is not right. It should be 3, yes. Do you remember the 2-bar mechanism? Okay, so regardless of if it's, sorry, I didn't show up here. I didn't show here, but anyway, even if there are 2-point loads, if it is a one span beam, the final collapse is 3 plastic hinges because of the 2-bar mechanism. Okay, there is only one possible condition. One possible condition is if this P is exact the same as this P. Okay, the 2 loads are exact the same and everything is symmetrical. Okay, if everything is symmetrical, yes, it is possible that there will be 4 plastic hinges. But if it is not symmetrical, there will be only 3 plastic hinges because of the 2-bar mechanism. Okay, so firstly, you need to bear this in mind. You have to keep this in mind. Okay, so the right answer is 3 plastic hinges. Yes, 3 plastic hinges. Okay, this is the first question. The second question I will ask, for this beam, which 3 points, there will be 3 points, right? Which 3 points will experience plastic hinges? Type it down, please. There will be 3 points, right? 3 plastic hinges. Which 3 points should have plastic hinges? Again, I said forget about these pictures. Forget these figures. Just based on this, based on your experience, based on your knowledge, based on your common sense, which location will experience plastic hinges? Let me check. 1, 3, 4. 1, 3, 4. Yes, exactly. Oh, some people say 1, 2, 4. Okay, 1, 2, 4. Yes, the right answer is support and maximum load. Yes. So it should be 1, 3, 4. Okay. Okay, so if you assume 1, 3, 4, and then you use kinematic method, you will get the right answer. Okay, but that story will be easy. So let's make the story difficult. Okay, let's make the story difficult. Let's assume the plastic hinge is here. Although it's not correct, it's not right, but let's assume the plastic hinge is here. And then you use kinematic analysis, and then you get PC, and the PC should be a upper bound PC. So in the next few slides, I will show you why. Okay, so this is a basic reason. How to say, this is an example showing you if you choose the wrong plastic hinges, you will get an upper bound solution of PC. Okay, and why the yield condition will be violated. Okay, so first of all, we have 3 conditions, right? So which condition are satisfied? The first of all, equilibrium equation, right? Equilibrium equation is always satisfied. And mechanism condition satisfied, because we have sufficient number of plastic hinges, regardless of the location. We don't care about location anyway. For now, at least the number of plastic hinges is correct. We have 3 plastic hinges to form a 2-bar mechanism, right? So the mechanism condition is satisfied. However, how about the yield condition? Yeah, this is the thing that we need to confirm. Okay, so we draw a bending moment diagram based on the selected plastic hinges, right? So this is a bending moment diagram. And we have MPL here, this is a plastic hinge. And we have MPL here. This is another plastic hinge. And we have MPL at point 4. So we have MPL at 1, 2, and 4 based on our selection. And what we need to determine is the bending moment at point 3, right? Because at this point, we don't know what happens. So the next step is that we use equilibrium condition to determine the moment at point 3. Okay. So what we can do, we have different ways. What we can do is we first isolate, we can isolate 1, 2. But anyway, so you remember the first step we need to do is getting the reactions, right? Do you remember when you're solving problems for beam, for either statically or statically indeterminate beams, when you try to solve problems in your undergraduate courses? Do you remember? The first thing you need to do is get the reaction, and then you draw a free body diagram of isolated beam, and then you use equilibrium, you can get everything. Okay, this is a basic step. It's the same here. It's the same here. So the first thing we need to do is to get R1 and R4. But anyway, if we get R1, we get R4 because of the vertical equilibrium. It's not a problem. So how we can get R1? We can isolate this part, 1, 2, right? We isolate this part of the beam. We draw a free body diagram. This is bending moment MPL, right? This is bending moment MPL. This is R1. We don't know the value yet. How about point 2? We have shear force here, but it doesn't matter because it will be cancelled out if we choose this point as a turning point. So it doesn't matter. And anyway, V2 is unknown. We don't know the value of V2. And we have another bending moment here, plastic hinge, so it's MPL again. Okay, so let's make equilibrium based on this. Let's make 2 as a turning point. So sigma M2 equals to 0. And then we can get this equation, right? If we make this a turning point, we have a clockwise moment exerted by R1. So R1 plus this lever arm, L over 3, equals to 2 anti-clockwise moment, right? MPL. Anti-clockwise moment, anti-clockwise moment. So we have this equation. It's a very simple equation. We can get R1. R1 is 6 MPL over L. Okay, so we get R1. And then, based on R1, what we can do? We can easily get this bending moment, right? We can have 2 ways actually. We can isolate this part, the left part of the beam, or we calculate R4 and we isolate this part of the beam. Both methods will lead to exact the same result. Okay, so it's up to you which part of the beam you want to isolate. But anyway, let's isolate the beam 1, 3. Okay, so if we make a turning point at so if we want to calculate the moment at point 3, so again we can use equilibrium. Basically, this moment here we can have R1 times this lever arm, right? This is clockwise, minus I think there'll be M2 MPL here, right? This is this is bending moment here, and minus this P also have a moment here. So P times 3 L over 3. Okay, these two are anti-clockwise, and this is clockwise. So they basically clockwise minus anti-clockwise moment. We get the final moment here based on equilibrium. The final result is 1.5 MPL. Okay, so based on equilibrium, we get the final bending moment diagram like this: MPL, MPL, 1.5 MPL, and MPL. Okay, so what's the conclusion you get? The yield condition is violated. right? Because we have bending moment larger than MPL, which is impossible. I mean, in real conditions, in real world, it is impossible. So the yield condition is satisfied. Yield condition, is violated. The yield condition is violated means, based on this, we only get an upper bound theorem. Okay. So anyway, let's continue. Again, let's continue. Again, this is the plastic hinges here. What we assumed for now, so far, what we assumed is plastic hinges here and here. Okay, so let's use kinematic analysis. Okay. So the first, the geometric relationship. This is delta. This is phi is half of delta, right? This is L over 3. This is 2L over 3. The overall length is L, and this is P, and this is 2P. Okay. So first of all, theta equals to 2 phi. Okay. This is geometric relationship. The work down by the external load P times H okay, this is P times H. This H is 2A over 3 phi. Okay, if we make a phi here, this is phi. Plus 2P times small h. L over 3 times delta. Phi. Right? This is a walk down by the 2-point loads. The walk down is 4PL over 3 phi. Okay, this is walk down. This is equation 1. What is energy absorption? Energy dissipation? So we have a plastic hinge here, plastic hinge here, and a plastic hinge here. So this one, MPL times delta plus MPL times theta plus phi, right? And plus MPL times phi. And we get 6 MPL times phi. And then we make equilibrium. 1 equals to 2. Equation 1 equals to equation 2. And we have this equation. And then we get P is 9. Remember, it's 9PL over 2L. Okay. So this is an upper bound solution. The equilibrium condition satisfied, mechanism condition satisfied, but yield condition, as I mentioned, is not satisfied. So what we get is an upper bound solution. Okay, so the real solution should be less than this upper bound solution. Let's say this P is PUB. UB means upper bound. Okay, PUB. Okay. So how about lower bound? Okay, we have upper bound. We can have a lower bound, and then the real solution is somewhere between upper bound and lower bound, right? So a lower bound solution can be obtained by reducing the loads and bending moments obtained by the mechanism method proportionally. And then yield condition is not satisfied, but the mechanism condition is not satisfied. I think let's still use this example. It's very easy. It's very easy. Lower bound is very easy. Okay. Lower bound is much easier than upper bound. The red line, do you see the red line? The red line is the upper bound solution and the resulting bending moment diagram, right? And then we just scale it down. We scale it down proportionally until every section is less than MPL. We scale it down and we get this blue line, right? So from here, 1.5 MPL, we reduce this to MPL. Of course, everything else is reduced proportionally. Okay, so if we look at the bending moment diagram of this blue line, how many plastic hinges now? You can tap it down. For the blue, the reduced or the scaled bending moment diagram, or everything is scaled down. How many plastic hinges we have now after scaling down? Yeah, only one. Only one. Okay. What if we assume 4 plastic hinges? I will answer this question later on. Okay. So only one. Yes. It's 3. Why? Why is 3? Can you explain why it's 3? Because look at the blue line. Blue bending moment diagram. Everything is scaled down. This is MPL originally, but we scaled it down. It's less than MPL, right? Again, this is less. So everything is, how to say, reduced by 1/3. But so we have only 1 plastic hinges here. Right? But yes, the moment is less than MPL now. So we now satisfy the new bending moment diagram, satisfy yield condition. But we now only have 1 plastic hinges now here. Mechanism condition is not satisfied. So we will get a lower bound solution. The lower bound solution is upper bound solution times 1 divided by 1.5. Okay, this is just the lower bound solution. It's very easy. We get upper bound solution, then we reduce it down by a necessary factor or by a necessary value, and then we'll get lower bound solution. Okay. So, if the upper bound and lower bound solutions obtained by the mechanism and statistical methods coincide or sufficiently close, the beam may be designed immediately. If these bounds are not precise enough, the original series of hinges must be modified and the bending moment determined, and the whole analysis has to be repeated. Okay, let's check the previous example. This example. Okay. So we get an upper bound solution. We get upper bound solution of 4.5, right? 4.5 MPL over L. What is the lower bound solution? What is the lower bound solution? Can you quickly type it down? You remember this equation? Okay, so what is the lower bound solution? Nobody? Yes. So it's 3, right? 4.5 divided by 1.5. Yeah, it's 3. So the real answer, because you are selecting the incorrect plastic hinges, so the real answer is somewhere between 3 and 4.5 MPL over L, right? Somewhere between this. So the lower bound and upper bound, they are not sufficiently close, right? So we're still struggling of finding the right answer. But anyway, what do we know? The good news is we know the real answer is somewhere between 3 and 4.5 MPL over L. Okay, but this is we still cannot get the right answer. Okay, so what you can do after class, I'm not gonna go through this in class. Can you try to find the real answer and prove this is the real answer? So you can assume plastic hinge happens here. Okay, so assume here. and then you get the right answer. Okay, can you try to do this after class? Let me know. Let me show the real answer is 3.6. This is the real answer. And you try to do that if you make plastic hinges here, here, and here, and you will get the exact result. Okay. So I would like you to do this after class. Okay. So let's make a short conclusion. If you select the right plastic hinges locations, and then you get PC based on the kinematic analysis method, and then you draw bending moment diagram, and you will find that the yield condition is satisfied, and then you confirm that you get the unique answer. Okay. So, however, if you choose the incorrect location of plastic hinges, and then you get PC based on kinematic analysis, and then you try to draw bending moment diagram, you will find that the yield condition is violated, and your result will be an upper bound result of PC. And then what you can do is you scaled everything down until the yield condition is satisfied, and then you will get a lower solution. The lower solution, bound solution, is the upper bound solution divided by the necessary number of scaling factor. And then you will get a gap. You will get a range. So what you will finally get is a range between upper bound and lower bound solution, and the unique right solution is somewhere between the two boundaries. Okay, so make a summary. This is the basic principle of these theorems. Okay, so try to do some exercises after the class, and then you will get what I mean. It's not difficult. Actually, it's not difficult. This part is not difficult. As long as you know how to solve problems, how to solve questions. Okay. Regarding the previous questions, some people say, okay, what happens if the two P are exactly the same? Okay, because of symmetry. I think the best thing you could do is, that's a little bit difficult. I think the best thing you could do is, you can try two plastic hinges, one here and one here, and then you have four plastic hinges, and then you have bending moment diagram like this, right? Let me try to. Okay, if this is a P, and this is P, so you have one plastic hinge here, one plastic hinge here, and one here, and one here. Then you have a bending moment diagram like here. Right? And this is MPL. This is MPL. This is MPL, and this is MPL. Right? And then can you use kinematic analysis to get P? P times this plus P times this equals to MPL times delta, 4 MPL times delta, and then you will get P. And then you check the bending moment diagram. The yield condition is satisfied, right? Because there's no point exceeding MPL, so you get the unique solution. Try to do that after class, okay? So it's very simple. Anyway, so let's move on. Do you want a quick break? Okay, let's have a 5 minutes break, okay? 5 minutes break. I think the only thing you need to do is to check this diagram, okay? So the red line is the upper bound. is a bending moment diagram when you get the upper bound solution, right? And then what you need to do, you only need to do is to scale everything down until the yield condition is satisfied, right? And then, based on the reduced diagram, which is the blue line, so you will see the plastic hinges number is reduced because this is originally MPL, right? This is small, now it's reduced, so it's smaller than MPL. This point again, it is MPL and then now it's smaller, and this is it was MPL and now it's smaller than MPL. So we only have 1 MPL here, which is reduced from 1.5 MPL, right? So it was reduced from 1.5 to 1. So we now only have one plastic hinge. Yeah. So that's the reason. Anyway, let's continue. So in the previous examples, the beams are mostly carried concentrated loads or symmetrical. And the position of plastic hinges can be located through observations and through guesses. However, in practice, different load patterns could exist, and determination of the collapse load becomes more difficult as the position of plastic hinges within the span can no longer be decided by a simple rule. Okay. Let's look at the example here. A propped cantilever is loaded with a uniform distributed load of W. Okay. The beam is uniform throughout and has plastic moment resistance of MPL for the cross section here. First of all, can you tell me how many plastic hinges you expect in this condition, in this beam? How many? Yeah, plastic hinges, 2. There'll be 1 here and 1. Okay. Can someone tell me the location of the plastic hinge in the span? Okay, there'll be a frictionless hinge here, a plastic hinge here in A. But do you know the exact location of the second plastic hinge? Okay, half of L. Somebody says half of L. Okay, anyone don't agree with this? No, yeah, somebody said no. Yeah. It's not in half of L. Yeah, because it's not symmetrical, right? It's not symmetrical, so it's impossible in half of L. But it's somewhere. Yes, it's somewhere near half of L, but it's certainly not half of L. Yes, because there is a moment at the point A, yes. So it's not symmetrical. Yeah, the reason why I ask you this question is we don't know exactly the location of the plastic hinge, right? But what can you do? What we can do is, okay, let's assume it's in half of L. And then we get upper bound and lower bound solution, right? And if the two solutions are close enough, yeah, maybe the real solution is somewhere between these upper bound and lower bound solutions. Okay, so that's at least a starting point that we could do, okay? So this is a gas bending moment distribution. And we don't know the location yet. Maybe somewhere here. But anyway, let's assume that a plastic hinge forms at a middle span, and we use the theorems to determine the upper and the lower bound solutions to the collapse load WC. And previously we said PC it's because it's point load, right? Concentrated load, PC. Now it's a uniform distributed load, UDL, so we call it WC. Okay, so first of all, we have two plastic hinges, one here and one here, and then we use a kinematic analysis. It's very easy. Let me quickly go through this. Okay, the work done by the applied load is WB, means upper bound. Okay, first we get upper bound, right? Upper bound solution times L, this is the overall load, and times the average displacement, which is L squared over 2 divided by 2. Okay, I have discussed this before, so I'm not going to go through this in detail. Okay, this is the average displacement, equals to works absorbed by plastic hinges, which is MPL times theta plus MPL times 2 theta plus 0. There is nothing here. So we have 3 MPL theta equals to WBL squared theta over 4. So based on this equilibrium equation, we get WB, upper bound is 12 MPL divided by L squared. So it's 12, okay? The number is 12 MPL squared. This is upper bound. Okay, can you prove this is the upper bound? Yeah, we can prove that, but now we don't need to prove that because we can prove that, but we know it must be upper bound solution because we know this location is not the exact location. Okay, if it is not the exact location, you always get upper bound solution. You remember that. You always get upper bound solution if you know that the location you selected is not the exact location of plastic hinges. So 12 is always upper bound solution. Okay, so let's continue. Equilibrium condition, don't worry about that. Mechanism condition satisfied because you have two plastic hinges to form a 3-bar mechanism, right? To form a 2-bar mechanism. So it's no problem. So it's upper bound solution. How about yield condition? Is it satisfied? We try to determine bending moment diagram to locate the maximum bending moment location. Okay, and it's a little bit tricky, but it's let's continue. It's a little bit tricky, but it can be solved. Okay, it can be solved. So now we have WB. Can you draw the bending moment diagram based on equilibrium condition? We have WB 12 MPa over L squared, right? WB. And now we draw a bending moment diagram. And then we try to prove that the yield condition is not satisfied. And then we scaled it down to get a lower bound solution. Right? So this is a procedure, this is a standard procedure that we should follow. Okay. So can someone tell me how to get the bending moment diagram? We know the shape of the bending moment diagram, but we want to get the maximum bending moment and try to prove it's larger than MPL, right? So we have MPL here, we have RA here, reaction here, then we have reaction RB here, we have UWB, which we already solved. Okay, so do you remember, if we want to draw the bending moment diagram, and if we wanted to... Sorry, can you give me 1 minute, please? I'm sorry. Okay, let's continue. Yeah, so what we can do is the maximum moment. Do you remember? The maximum moment means the shear force is 0, right? So if we can get the shear force, we can get an equation regarding the shear force and make it 0. We can get the location of the maximum bending moment, and then we again use equilibrium. We can get the maximum bending moment. It's a little bit tricky, as I said, it's a little bit tricky, but you should understand that, because again, this is undergraduate courses, the problems in undergraduate courses. You should be able to solve this, okay? But anyway, let's quickly go through the procedures, and if you could not follow me, you check it after class, okay? Because this is a knowledge you should already know in your undergraduate courses. So I'm going to quickly go through this. The moment at point B, first you need to calculate RA, right? You could calculate RA, so you make a turning point at the moment at point B, and then you have RA times L, clockwise moment, minus anti-clockwise moment MPL, minus anti-clockwise moment exerted by WUB, the WUB times L times half of L. Okay, so if you make this equation, you will get RA, okay, because you know WUB is 12, right? 12 MPL divided by L squared. So you know you get RA, which is 7 MPL of L. Okay, so this is RA. And then if you get RA, can you quickly get the equation of bending moment or shear force with X, right? Because this X equals 0, and then this is X along the length of the beam. The position X of maximum bending moment can be determined by using equilibrium condition, and shear force equals to 0. So if we isolate the beam again, so can you get Vx? Okay. Vx equals to, we use equilibrium in the vertical direction, Ra minus Wb times x, right? And then we know Wb is 12 mp over s squared, and we know Ra, so we can get x. If we make Vx equals to 0, we get x. And then we get x, then we can calculate this x is maximum bending moment location, and then we again use equilibrium. We can get the moment at x, which is Ra times x divided by MPL, then divided by Wb times x times xo over 2, right? Okay, I quickly go through this. You should be able to understand this, okay? So based on the first equation, we get x, we get x is 7a over 12, and then we get the maximum bending moment here, this equation. So we get maximum bending moment 25 MPL over 24. Okay, so this is the final result. So x happens here, 7L over 12, and based on the equilibrium, we get the maximum bending moment here is 25 MPL over 24. Okay, so this is the final result. Because we know the shape, right? We know the shape of the bending moment diagram. So what we need to do is get the maximum bending moment, and then get the location of the maximum bending moment, and then get the value of the maximum bending moment. Okay. I know some of you may not be able to follow everything here, right? But again, I leave this to you after the class, okay? Because I will send you the PowerPoint slides. You try to understand by yourself after the class, because this is not the focus of this lecture, okay? So assume you understand everything here. But anyway, we get M max, which is larger than MPL, right? So you can see that the yield condition is not satisfied. right? So the upper bound solution, 12 MPa over L square, is the upper bound solution. And how about the lower bound solution? Sorry. Anyway, okay. How about the lower bound solution? Okay, can you tell me what's the scale factor? The scale factor to get the lower bound solution. Actually, the answer is here, but I would like you to type it down. Okay, this is the upper bound solution. 12. Can you tell me the lower bound solution? Do you want to scale it down? Do you want to scale it down? If you scale everything down of this bending moment diagram, what's the scale factor that you want to do until the yield condition is satisfied? Yeah, it's 24 divided by 25. So this is the scale factor. Why somebody say 8? What is 8? Yeah. Okay. Good. So the reduction factor is 24 over 25, so approximately 0.96. Okay. This is a lower bound solution. But if we scale everything down, we only have one plastic hinge now because this is reduced from 25 to over 24 to 1, right? It's reduced to MPL, and this is, so originally it was MPL, but now it's smaller than MPL. So there is only one plastic hinge here, so the mechanism condition is violated, but the yield condition is satisfied. So now we have a lower bound, okay, 0.96. It's a reduction factor. So the mechanism condition is violated after reduction. The lower bound solution is here, 0.9496 times 12, which is 11.252. Okay. So now, what's the range? So the real solution, can you give me the range of the real solution? The real solution is from, sorry, say it again?
11.52 to 12.
Yes, it's somewhere between these two values. Okay, actually, if I'm an engineer, I'm happy with the result, right? Because 11.25 and 12, this range is sufficiently small from my point of view. It's already very small. So, okay, if I'm an engineer, maybe I would say, okay, somewhere between, maybe it's 11.7, maybe, or 11.8. I don't know, maybe this is the final result. So if I'm an engineer, I'm not gonna go repeat the calculation again. So I will take a guess value, maybe say, let's say 11.7. Okay, so you can do that, it's fine, it's totally fine, because the upper bound solution and lower bound solution now is very close to each other. Okay, so it's up to you, it's up to the engineers to determine if a repeated calculation is needed. Let's look back the bending moment diagram somewhere, something like this. Okay, so if you want to repeat your calculation, it's fine. Originally, you assume your plastic hinges happens here, right? Now you just move it a little bit to here, maybe say 7.7 over 12 of length L. Okay, and then you do everything again. I think you will get very, very close, small range, a very close lower bound and upper bound solutions, very close. So it's up to you. You could repeat everything again by adjusting or by changing a little bit of your location of plastic hinge. Or you could say, I don't want to repeat the calculation because the upper bound and lower bound solution are close enough. I'm happy with the result, so I can guess a result. It's fine. So it's up to you, okay? So this is the basic principle of what we could do in when we design or when we determine the real the true answer. Okay. So the question is, how can you determine the true unique value of the Krebs load? Yeah, I leave this to you after class. If you're happy to repeat everything again, you could do that again. So, in conclusion, the unique solution can be obtained by trial and error. So you can try by observing the bending moment distribution. Okay. It may not be straightforward, but every iteration, every repeated calculation, you will be closer to the real answer. So design aspects, okay, so I leave this to you after the class, okay, so I'm not going to go through this. Just try to quickly go through this after class. Here are some exercises that you available for you to do after the class, and I think these are the answers that you could check the answers. Try to do that after class, okay? Okay, so I think this is the first half of today's lecture. Let me start the second half. There's some chat room. Okay, I think maybe we can skip the break, okay? So we continue and we can finish the class earlier. Okay, are you happy with that? Okay. Let's continue. Yeah. Again, submit your homework, which I will send to you after the class, together with today's PowerPoint slides, and you submit your PDF format homework to this email address by the end of October. Okay. Now let's move on from a beam to a portal frame. Actually, portal frame is also very easy. It's also easy, it's not difficult. So don't worry about that, it's not difficult. So previous beam examples are all loaded in vertical direction. Okay, so this lecture will focus on the structural behavior of rectangular portal frames subjected to both possible vertical and horizontal loadings. And let's investigate different possible mechanisms first. Okay, the good thing for a portal frame is there are only 3 possible mechanisms. Do you remember for a beam, the most typical one is 2-bar mechanism, right? This is the most typical one for 2-bar mechanism. Similarly, for a portal frame, we also have 3 typical mechanisms. And the first thing that you need to remember is understand the 3 typical mechanisms. And then, based on the 3 typical mechanisms, you use virtual work, you use kinematic method, right? And you get 3 PCs, right? You have 3 mechanisms, you remember these 3 mechanisms, and you get 3 values of PC, right? Based on these 3 mechanisms. And then you compare the 3 values of PC, and then you choose the smallest one. And the smallest one is the right solution. So this is the basic procedure to solve a problem in a portal frame. It's not difficult, right? The only thing is you understand the 3 mechanisms. So depending on the relative magnitude between horizontal or vertical loadings and the portal frame configuration, the following mechanisms are possible. 1, beam mechanism. 2, sway mechanism. And 3, combined beam and sway mechanism. Okay. First, let's check the beam mechanism. Again, look at this example. We have a portal frame. Sorry, it's not in scale. It's not in scale. But don't worry, this is a dimension. So we just check. We follow the dimension. Okay, it's not scale. So the height of the portal frame is 0.6 L, and the span of the portal frame is L. We have a horizontal load applied here, P, and we have a vertical load applied at the middle span of the portal frame beam, 2P here. Also, the portal frame has the column and the beam are different in section. So the beam section is stronger. Okay, the beam section is stronger, and the moment resistance, plastic moment resistance of the beam section is 2 MPa. The column is a little bit weaker, so the moment resistance of the column is MPa. Okay, so first this is example. This is the beam mechanism. So at the point load, we have plastic hinge at 2 supports of the beam, and 1 plastic hinge in the middle span. Okay, so this is a typical beam mechanism if a point load exists along the member. So this is a possible. So these are some other possible examples. Okay, look at this one. If there is a point load here, there will be a beam mechanism here. Okay, so it doesn't matter if it is a horizontal or vertical direction load, as long as there is a load along the span of the column or beam, we call it a beam mechanism. It's like similar to the 2-bar mechanism in a beam, right? Okay, so we have 3 plastic hinges here. One thing that you should keep in mind is, maybe some of you have already noticed, this is a little bit strange, right? It looks a little bit strange. Why it looks like this? Okay, can somebody tell me why it looks like this? It seems that the plastic hinge happens in the column, not in the beam. Why this happens? Why it doesn't happen like this? Okay, somebody may say, okay, let's draw like this. Okay, it looks more reasonable. Okay, this is the case if everything has the same cross section, because the column, beam, they have the same cross section. Okay, it's fine. However, here, you see, the column is weaker than the beam. The plastic hinge must happen in weaker sections. So it happens in the column. Actually, the only difference for you is when you try to use kinematic analysis, when you try to calculate the energy dissipation, you use MPL, not 2 MPL. So that's a major difference. Okay, the other thing is exactly the same. Okay, let's look at the equation. The walk down first is 2 PC. Okay, so there's something missing here. Anyway, times this distance, which is L over 2 times delta. This is delta, right? This is delta. Plus PC times what? Nothing here. Because of the beam mechanism, there is no sway, deformation or displacement of the portal frame. So the walk down by PC by the horizontal load P is 0 because there's no displacement here. Okay, so the walk down based on the beam mechanism is PBL delta. How about energy dissipation? We have plastic hinges here, here, and here. The energy dissipation, this one, MPL, it's not 2 MPL, it's MPL, because the plastic hinges happens in the column. So if in case somebody don't understand, plastic hinge happens here, right? Happens here, and happens here. Okay, so it happens in the column. The energy dissipation, this point, MPL times delta. This is delta. And 2 MPL. Now, this is beam. So it has to be 2 MPL. It's not 1 MPL, okay? It's 2 MPL because this is a beam. And times 2 delta. Plus MPL times delta. So overall is 6 MPL. So based on this equation, we get the collapse load PC, which is 6 MPL over L. Okay, this is a PC calculated based on the beam mechanism. So we say it's PCB. Okay, remember this symbol. We use PC, comma B. B means beam mechanism. Okay. So this is the first value of PC we get is 6 MPL over L, the first value. Now let's move on to the second case, possible case. Yeah, I'm gonna do that again. Okay, sway mechanism. Sway mechanism is like this. It looks like, the frame is about to lose stability, right? It appears like that. Okay, again, somebody says, this is strange. Why it happens here? Again, this is because of the weaker column. Okay, if the column has the same cross-section as beam, it will look like this. But the column is weaker, so it will look like this. So can we quickly go through the equation based on the kinematic analysis? It's very easy, right? So based on the predetermined sway mechanism deformation mode, the horizontal load PC has some displacement now, which is, assume these angles are theta. So it's PC times 0.6, right? 0.6 L, 0.6 L is the height of the frame times delta, right? This is this displacement, horizontal displacement. How about vertical load? The vertical displacement is 0 for a sway mechanism, so there is no walk down by this vertical load 2P. Okay, so this is a walk down in this case. Similarly, the energy dissipation, MPL times delta plus MPL times delta, because this is a column. Okay, plastic hinge happens in the column, plus MPL times delta plus MPL times delta. So it's 4 MPL times delta. So we get the second value, PCS. S means sway mechanism. So 6 times 7 MPL over L.
Hello, sir.
Yeah.
Please, I have a question. I want to ask, why don't we consider the sign convention of the angles? I mean, the plastic hinges, because you know that, as you know that if the angle is opening or closing, the signs are not the same. And if, for example, I want to add, the plastic hinge of the beam mechanism and sway mechanism, don't we have to consider the sign if it's positive or negative?
No, because energy is always absolute value. This is energy.
I mean, if for example, in case we want to add like the two plastic hinges, because we said that we may consider different cases. What if we want to add like two angles? Don't we have to consider the sign?
Sorry, I didn't quite get what you mean.
For example, okay, because you said like there's beam mechanism and sway mechanism. According to the undergraduate, when we used to do like the analysis, sometimes we might add beam plus sway mechanism, right? And if, for example, we want to find the final angle, we might have like minus theta and plus theta. So it means these two angles are going to...
It's not applicable to the condition, because, for example, the walk down, right? You mean the walk down, there's no positive or negative value of delta. It's just the delta. As long as there is displacement, it's just delta. So you don't need to worry about the positive or negative value. It's always positive. Similarly, for the energy dissipation, it's always positive, because energy, it doesn't matter it's positive or negative delta. So in this case, we don't need to worry about positive and negative. It's always positive. I'm not sure if I answer your question, but
actually my question was in case we want to add later, for example. I don't know. Yeah.
Anyway, so if you have some specific question, you can draw it. Maybe after class we can discuss. Okay.
Okay.
Yeah, because at least for now, I don't see any particular reason why we need to worry about the sign of the angle. Okay, so let's move on. Okay, the third mechanism. This is a little bit tricky actually. We call it combined mechanism. So it's a possible combined sway and beam. It is possible. Okay, so it fails like this. So there will be a sway like this, right? Like a sway instability. And there is also a beam mechanism like this. Okay, the only difference is for a beam mechanism, let's look at this picture. For a beam mechanism, there will be plastic hinge happens here, here, and here, right? This is a typical beam mechanism. And for a typical sway mechanism, it will be here, 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 and here. And for a combined mechanism, it will be like here, 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 and here. Okay, so people say, why there is nothing here? Because you see the geometric configuration, okay? The column moves this way, the beam moves this way. They are all experience as a clockwise, rotation or whatever. So the bending moment here will be very small. So finally, we'll have a combined mechanism like this. Okay, so can you try to understand that? Yeah. Anyway, so you just need to remember this is a combined mechanism. Okay. And if you look at the geometric relationship, if the column inclined by theta, and this column again inclined by theta. Okay. So how about the absolute angle here? And how about the absolute angle here? This is zero. There's nothing happens here. There's zero change in the angle. But based on the primary school knowledge about geometry, can you tell me what's the absolute change of the angle here? Is it theta? Or is it 2 theta? Or is it 3 theta? Nobody?
2 theta.
Yeah, it's 2 theta. Similarly, this is also 2 theta. Okay, so it's 2 theta, and this is 2. Because this is a little bit strange. You may not get this very quickly, but you can check this This is more straightforward, okay? So again, let's make equation. The walk down is, okay, because it's combined, both horizontal and vertical load causes work. They produces work. So PC, the horizontal one, times 0.6 L times delta. This is distance, plus 2 PC times this is delta. It's a beam sway mechanism. It's a beam mechanism, right? So it's L squared over 2. Don't get this. And the energy dissipation, we have 4 plastic hinges here. MPL times delta. This is 2 MPL times 2 delta. And this is MPL times 2 delta because it's column. Plastic hinge happens in column. So it's MPL times 2 delta plus the column base, MPL times delta. So it's 8 MPL side. So the final result, PCC, C means combined, is 5 MPL over L. Okay? So now let's make a conclusion. Beam mechanism, and we get the value of 6. Sway mechanism will get the value of 6.67. Combined mechanism will get 5. So what's the final answer?
Combined.
Yeah, it's combined mechanism. It's combined because it had the smallest. It's critical solution, we call it critical solution, so it's 5 MPL of L. Okay, so before we try to prove this is a unique solution, let's make a quick conclusion like here. Okay, so beam mechanism, so we're assuming column tops remain stationary and no sideway movement. So all deformation caused by hinge rotations. So the position of plastic hinges could be one plastic hinge within the span of beam mechanism. And depending on the relative strength between beam and the column, 2 plastic hinges could at either end of the beam or top of columns. Okay, and the kinematic analysis results is PCB. Sway mechanism, all deformation caused by hinge rotations. And position of plastic hinges could be 2 hinges at the column base, and depending on the relative strength, other two hinges either at ends of the beam or top of the columns. And the collapse load is PCS. Finally, combined mechanism is the combination of the two. Okay, so this is the conclusion. So now let's prove this one is a unique solution. Okay, is PCC, it has the smallest value, but is this a unique solution? Again, we need to check 3 conditions: equilibrium, mechanism, and the yield. Equilibrium condition is always satisfied. Mechanism condition, okay, if we follow the recommendation of the 3 mechanism condition is always satisfied. Okay, so sufficient plastic hinges leading to a combined mechanism. So the only thing we need to check is a yield condition. Okay, let's draw a bending moment diagram first. For a combined condition, let's move back. We have a plastic hinge here, 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 and here. Okay, so at least we know this is MPL. Sorry. This is MPL, this is 2 MPL. This is MPL, this is MPL. Okay, so we know the bending moment at these 4 critical positions. So the only thing we want to check is the bending moment here, right? And then we can draw the bending moment diagram. Okay, this is MPL, as I mentioned. This is 2 MPL. This is MPL. And because of the equilibrium, so this must be MPL as well, because we have equilibrium at 0.3. And also this is MPL. Okay, so the bending moment diagram is something like this. Okay, so something like, but M2 0.2, we don't know that yet. So what we want to do is want to determine M2. Okay. So MPL, this is the 1.1, 0.2, 0.3, 0.4. Okay. Something like that. Okay, can we calculate M2? First thing first, what do we want to get? Reactions. Right? Okay. Actually, there are different ways, different paths, different routines that you could follow. Different people have different way to solve this problem. Okay, so maybe first you may isolate member 3, 4. It's up to you how to start. You can isolate members 3, 4, and then you can calculate H4, the horizontal reaction H4, because we have a horizontal load here, right? So we can calculate H4. So let's start. We isolate member 3, 4. Okay, at the column base, we have a horizontal reaction H4. We have vertical reaction V4. It doesn't matter about direction. So we can calculate, guess the direction, but actually it should be upwards. But anyway, it doesn't matter. And we have a bending moment here, MPL, right? We have MPL here. At point 3, we have a vertical load, V3, horizontal H3, vertical V3, horizontal H3, and MPL, right? So actually we can make 3 as a turning point, or make 4 as a turning point to get the same result. Let's make a 4 as a turning point, okay? Let's make this point as a turning point. So we have MPL, MPL, and then which should be balanced by H3 times 0.6L. Okay, so based on this simple equation, we get H3, and then we get H4. H4 equals to H3, right? Because in this isolation. So anyway, as I said, different people have different ways. Okay, so don't worry about that. You may have you may use different way to get the exact same result for H4. Okay, so H4 is 10 divided by 3 MPL over L. So we get H4. After we get H4, we can get H1, right? Because of the equilibrium in the horizontal direction. Because we know PC. We know PC is 5 MPL over L. Yeah, we know PC, so we can get everything. Okay, so we know PC and we know H4 now, so we can get H1. Okay, so we get H1. So if we get H1, you will do? You can just isolate 1, 2, this member, right? And then here, you isolate member 1, 2. You have H1, which is this H1, and you have MPL, right? You also have some vertical or horizontal force here, and you have unknown moment M2 here. Okay, so you can make a moment at point 2, and you will get M2, which should be balanced by H1 times 0.6L. This is clockwise, and divided by minus the anti-clockwise moment MPL. Okay, so you will get your answer 0. Okay, this is the final answer. M2 is 0. So can you draw the bending moment diagram like this? It's 0. So check the yield condition. Is yield condition satisfied?
Yamaha. What is?
Is it satisfied? Yes or no? Have your result? Yes or no? Anyone? Anyone? Is yield condition satisfied? Yes,
Yes,
or no?
yes.
Yeah. Yes. So you say yes. And yes, it's yes. Although this is 2 MPL, but it doesn't matter because this is beam, right? So it should be maximum 2 MPa. So yield condition, yes. So PCC, unique solution, right? Very simple, very simple. So I think that's what you need to understand for calculating a Portal frame. Okay, so okay, let's skip this. So let's make a summary. Okay, for exercises, you can try to do it after class. Okay, try to do it after class. The summary to plastic collapse analysis. So in last week, we have discussed the fundamental concepts, redistribution of internal forces in statically indeterminate structures, and plastic bending, plastic hinge, plastic section modulus, shape factor, blah, 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 something like that. And then we've moved on to rigid plastic assumption, and we introduce the most important approach, kinematic approach. Okay, and in today's class, we introduced the 3 conditions: equilibrium condition, yield condition, and the mechanism condition. And for a beam, we have a uniqueness theorem, upper bound theorem, and lower bound theorem. Okay, and then we move on to the collapse analysis of rectangular Portal frame and the vertical and horizontal loadings, and then we introduce these 3 mechanisms: beam mechanism, sway mechanism, and a combined mechanism. And then you use kinematic analysis based on the 3 mechanisms to obtain 3 values of PC, and then the critical one is the lowest one. Okay, and then you try to prove that check the bending moment diagram and confirm if this is a unique solution or not. Okay, so this is the basic concept. What I would quickly go through before ending today's class is the application of plastic analysis. Okay, so in real design practice, what we could do, how we can use the plastic analysis to try to solve problems. So first, I would like to say capacity design. Capacity design is a mainstream design approach today. The capacity design was developed in the 1960s in New Zealand as an approach to resist the effect of severe earthquakes. Because under normal loadings, it is quite impossible that a plastic hinge is fully developed. Because in design, we try to avoid a formation of plastic hinges. But on the earthquake, it's totally different story, because on a severe earthquake, everything could happen, right? The building will experience extensive damage as well as extensive distributions of plastic hinges within the frame, for example. So it's very important in earthquake engineering practice. So many aspects of this philosophy are embedded in many code requirements. Okay. So here are some concepts, okay, that for you to understand. So first, we need to acknowledge the inelastic action is unavoidable during severe earthquakes. It must happen. The plastic zones should be selected to be regions where large plastic deformation can develop without significant strength loss. So by making the capacities of the surrounding structural members greater than that needed to reach the maximum capacity of the so-called plastic zone, the likelihood of inelastic action or failure will be eliminated. So basically what we do is we try to create some fuses. During those fuses, we try to create fuses and make these weak locations experience plastic hinge first, and in order to dissipate energy. So the whole system could stay, but may not collapse. Okay, so this is the main design principle. Okay, so in theory, once a fully plastic state has been reached, no additional force can be resisted by the structure. So as a result, the regions outside the critical plastic locations are protected against the effect of additional loading. So basically, we have a fuse, right? So you can try to understand this figure. It's a very simple figure, and so it's basically we create a weak area and make plastic hinges happens here. I'm not going to go through this. You can try to do it after class. Okay, so if we look at a portal frame again on the earthquake condition, so basically in real design, what we want is we want plastic hinge happens in the beam. Okay, because of the strong column and the weak beam theory principle. And then the column hinge, the column base, yes, we can also have some plastic hinges. So this is basically the desired deformation mode of a portal frame on the earthquakes. We don't want plastic hinge happens in the column. Too many plastic hinges happen in the column because this will lead to earlier collapse of the system. Okay, especially when we say soft story failure mode. Okay, we must avoid soft story. So what we want is like this. Okay, what we want is like this. We want to avoid soft story. But this is some additional information for you to understand. It's not necessarily related to our previous slides. Okay, so that's some additional information for you guys to understand that in earthquakes we cannot avoid plastic hinges, but we want plastic hinge happening at the locations where we want. Okay, in order to keep the structure safe. So this is the basic concept in earthquake design. I think that's all for today's class. So try to submit your homework. Okay, again, I highlight this again. I think that's all for today's class. So do you have any particular questions for me before ending the class? Yes, please.
Like about what we were trying to discuss about the sign convention. Maybe I just try to draw an example. Let me just send it maybe so.
Okay, I can